welcome to the technical lecture from NCT. It is the second lecture series of lectures from Mr. Athavale on mold and core coatings. And today's subject is selection and application of mold and core coatings. We all know Mr. Athavale as an expert in foundry engineering with a Master of Engineering program in Foundry Sciences from Indian Institute of Science, Bangalore, and an experience of more than 30 years in developing products for various applications in ferrous and non-ferrous foundries at Messrs. Foseco India Limited. Mr. Athavale is an authority on any subject related to foundry. He retired as Head of Technology and Marketing and continues to work as consultant for technical training as well as marketing. The co-author for an educational DVD on the refractory coatings for ferrous and non-ferrous applications for NCTS and presenter of papers at seminars of Institute of Indian Foundrymen and other industry associations. Mr. Athavale will now lead us in today's topic. Over to you, sir. Thank you.
Good afternoon to all of you. After our problems last Tuesday, let me quickly go through the initial slides, which many of you have seen. We will do a quick recap of what we did in the last lecture, what we covered in last lecture. Then we will look at selection of mold and core coatings, then coating application methods, equipment, and process control. Then drying of coated cores, and then we will summarize our today's lecture. A quick recap. Casting finish and role of coatings. Now, surface finish, as most of you know, is a very, very important parameter for acceptance of castings by the casting buyer. And that it can have two reasons. One is the functional aspects and another is aesthetic aspects. As an example, here is enamel layer where casting has to have a particular level of roughness so that you are able to provide the enameling, which is a coating on the surface of the right quality. The other example that we saw last time was about turbocharger housing, and we saw that as the average surface roughness increases, the efficiency of the turbocharger drops down in this particular stream by as much as 4%. That is because the Reynolds number is affected by the roughness. Then we looked at the surface comparators, which many of you will be familiar, and these are the visual comparisons which correspond to a particular sort of RMS value and can be used for checking the surface roughness of the casting in a given area. Now, what are the factors that impact the surface finish of the casting? And those are metal factors and mold factors. So these, the interaction between them, the mold and the metal, gives you a particular type of surface roughness, and it also has a bearing on presence or absence of surface defects. And we saw the physics and chemistry behind the surface roughness as well as some of the casting defects. And we saw that there are two opposing forces which are working when it comes to surface roughness or when it comes to metal penetration, as we call them, penetration of the metal between the voids in the mold or core surface. So when the metal enters the mold or core is experiencing three types of pressures. One is the gravitational pressure because of the head height of the metal in the mold. The other one is the dynamic pressure because of the velocity of the metal. And third one can be, in some cases, the pressure of expansion of the metal as it solidifies, as happens in case of gray iron. It may not happen in all the cases. And what are the forces which are opposing this pressure on the sand or mold face? One is the capillary forces, the other is frictional forces, and third is the pressure of the gases which may come out of the molding media. And we looked at those equations and we said that if the dynamic pressure and static pressure exceed the capillary and frictional forces, then you will get what we call as mechanical penetration. If, say, in case of steel, the iron gets oxidized and then it reacts with silica of the molding medium, then it forms a low melting phase called fayalite, that is FeO plus twice FeO plus SiO2 giving you fayalite. And that is termed as chemical penetration. Wettability of the metal because of this chemical reaction encourages the penetration of the metal into the sand surface. So these two are for metal penetration. Then as the sand surfaces, sand layers get exposed to the heat of the metal, the top layer in the immediate contact with the metal will initially expand as silica undergoes phase transformations. And beyond 573, it actually starts contracting. So the top layers will start contracting shortly after they cross that 573, 575 degrees, while the lower layers are expanding. So if the upper layers are not held properly, then they will tend to crack open and form veins, as has been shown here. We looked at the mechanism of vein formation in details last time, so I'll not spend too much of time on that. If the refractoriness of the sand aggregate for mold or core have poor refractoriness, it has some low melting phases, the chemistry is not right, then at the casting temperature, the sand may fuse onto the surface. Or other way around, if you have too much of excess superheat, then again you can land up with sand fusion problems. Here is a schematic about what is the role of the coatings in providing a particular type of casting surface finish. This also we saw last time. As you can see, when there is no coating, the metal mold surface is more uneven. It is rougher. And the resulting metal surface after knocking out the casting will be rough like this. When there is a coating layer present, the filler particles will get in between the sand pores, plus there will be a layer on the top of the mold. So a smoother surface will be offered to the metal. As a result, casting will have a smoother face as compared to the little more rougher, jagged surface appearance. Then we looked at what are the constituents of a coating. And the key ingredient, of course, is the refractory fillers, because these are the working fillers which will go on the top of the sand mold and core as well as fill the voids in the sand surface. They are bound to the surface mold or core by use of binders. There are suspension agents which keep the refractory fillers in suspension in the liquid carrier that is being used, because that is what will carry the filler to the mold surface. And then there will be additives, which can be preservatives in case of water-based coatings, or they will be viscosity modifiers, which will give a right kind of viscosity behavior depending on the method of application of the coating. The additives will also be wetting agents so that they will allow the coating to adhere to the surface of the mold and core. So we had a look in detail for this. Generally, it will be fair to say that coating formulations are designed very carefully to achieve good casting finish by having a right proportion of right type of constituents to get a balanced performance for given type of casting as well as method of application. A quick look at viscosity behaviors. At the top that we see is called as thixotropic behavior, which is useful for brushing or swabbing, where on application of the force to the body of the coating, the viscosity drops gradually. So as the viscosity drops, the coating starts flowing onto the surface, and as you remove the brush or the swab from the surface, the viscosity goes up again, but it doesn't go suddenly. It takes some time before it reaches the original level, and that allows the brush marks to level off to an extent. While another case of thixotropic behavior where the drop in the viscosity is very, very sharp on application of the force onto the coating body, as in case of dipping. To take a core and dip it into the coating tank, there will be a sharp drop in the viscosity, as you will see from the arrows here. And so long as that shear is being, constant shear is being applied, the viscosity will remain low. As you withdraw the core from the coating bath, the viscosity sharply goes up and the coating stays onto the surface of the core that has been dipped. Same logic to an extent would apply in case of flow coatings as well, though slightly modified. Now let's look at selection of coating for a given application. And here are selection criteria. So how do you go about selecting the coating constituent? And what are the factors which impact or which decide the choice of the filler or filler combinations? And how do you do that? So filler are largely governed by casting metal chemistry and casting size and geometry. Why casting metal chemistry? Because that decides the melting temperature and pouring temperature. So what level of refractoriness is needed, and metal mode reaction tendency. Chemistry also decides metal mode reaction tendency. In our last lecture, we had seen the phalite formation reaction, or in case of manganese steel castings, how manganese oxide, manganese silicates, they would be forming by reaction with silica sand. And casting size and chemistry decides the metallostatic pressure and not chemistry, geometry, hotspots. So this again will help define what level of refractoriness we want and how much resistance to the pressure we need. Now carrier selection. We saw last time we can have 2-3 different types of carriers such as water and spirits and any other special solvents. Now the selection of carrier is largely governed by the type of binder, because the carrier that you choose has to be compatible with the sand binder. If it is not, if the carrier is going to attack the binder, then it will degrade the core strength and or mold strength, and it will create surface friability. So you need a carrier which is compatible with sand binder system. It also is affected by what are the facilities available for mold or core drying post coating operation. So that also will have a bearing on carrier selection. And then method of application of the coating as well as type of carrier, they will decide the gel system. The binders are decided by what kind of carrier you are using, and specialty additives are decided by what is the method of application. Is it going to be brushing, swabbing, spraying, dipping, or overflow? Because viscosity behaviors will have to be adjusted as per that, for which you need specialty viscosity modifiers. Also, how, say, for example, for water or water carrier coatings, how wettable or non-wettable is the core surface also will decide what kind of surface wetting, surface active agents, wetting agents need to be used or not. And method of application in turn is governed by size and geometry of the mold and core, as well as the number of molds or cores to be coated, and obviously mold and core handling systems which are available. We will see little more details as we go forward. Fillers. Here is a quick look at fillers and the casting alloy. For carbon steel, most common one is zircon. You can also use magnesite and olivine from refractoriness point of view. For alloy steels, again, same three will be applicable. All of them, because we have seen the details, physical properties of all these fillers last time in our previous lecture. What are their melting points, fusion points, etc., sinter points. For manganese steel, you need something which is non-siliceous. So, magnesite-based coatings, that is MgO-based coatings, and olivine. And again, we looked at what should be the filler properties in our last lecture. For cast iron, a combination of all of these fillers gets used depending on what is the end application, what results you are looking at. As an example, a very broad classification, if you are going to produce a very large iron casting where the head height is more, then a combination of graphite plus zircon is what will be used for that coating. While when it comes to say cylinder heads where you are using cold box as a coating, then you may use combination of aluminosilicates, mica, etc., and silica. In fact, in some cases, some proportion of even iron oxide will be used for specific purposes. Copper alloys, most of the fillers are useful. For aluminum also, most of the fillers are useful. For magnesium alloys, which are very, very aggressive, magnesite and olivine are the two types of fillers which are required to be used for magnesium alloy coatings. I will once again repeat, depending on the section thickness and weight of the casting, a combination of fillers may have to be used. In practices, we will see little more. These are general guidelines. For a given casting, for a given foundry's way of producing them, sometimes a coating supplier will make a customized formulation just to meet their specific requirements. As far as carriers are concerned, it is pretty simple. If it is green sand mold, as is the practice with in many green sand foundries on high pressure molding lines, if the head height is large, say for a casting like engine block, the drag surface you may get metal penetration. And to avoid that, then one will have to use an appropriate coating, maybe a graphitic coating with alcohol as a carrier. While if it is organic binders, like you have alkali and phenolics, or you have your furan binders, or your other variety of types of organic binders, including you may have pepsite and you may have cold box, and for which water is the preferred binder, assuming you have proper drying facilities. Because why for organic binders water? Because the binder is affected by alcohols. For sodium silicate binder, as all of you are familiar, sodium silicate readily dissolves in water. So people prefer to use solvent-based coatings for that. That is either methanol, ethanol, IPA. We saw details of their properties last time. Now let's look at method of application of coating and what are the process controls which are needed. Selection of what is the method of application is governed by size of mold and core to be coated, number of molds and cores to be coated, plant layout and availability of equipment for mold and core handling, environmental considerations, casting surface finish requirements. So these are the main factors which decide method of application. Now, here are 5 different ways in which the coating can be applied. One is brush and swab, which is largely used for, most commonly used for medium and large size molds, where the numbers will be limited. Spray is generally used for where the production is on a higher side, though it can also be used in jobbing, but more commonly used in slightly higher production levels. The numbers are more. Then before getting into electrostatic deposition, let us get to the dip and flow. Dip is typically meant for mass production, high volume, small size or medium size cores. So it can be manual application, it can be semi-manual, or it can be fully automated dipping operation. But the numbers are very large. The core shapes can be complex, or so dipping is the best way, because either swab or brush will take too long a time, and we'll see one by one merits, demerits of each one of them. When you go towards medium or large size molds and cores, then flow coating is becoming more and more popular because of its inherent advantages over brush and swab. But then it has its own requirements of what type of equipment is needed, because it does require equipment. We'll see these one by one. A few words on electrostatic powder deposition. It is not very common in foundries, though long ago when I was handling this coating development in Foseco in 80s and 90s, there was a technique which was developed for electrostatic deposition of the coating onto the surface of the clean sand molds. That is what we had tried. It used to work okay, but it required a lot of automation and a lot of optimization. So it did not become very, very popular in foundries for mold and core surface, though I'm sure new techniques always evolve. Now swabbing application, and let's see if you are able to see this video. Here is a gentleman, a worker, who is applying the coating on this big mold by using swab. So long as there is a horizontal surface, he is able to nicely rub the coating in. While as far as vertical surfaces are concerned, he just about sort of touches it, there is no great pressure that he can apply there. In brushing, yes, you can, but not so much in swab. Let's look at few key points. Because there is an effort which is imparted by either brushing or swabbing, you are able to force the refractory particles into the pores of the sand surface, which is a desirable feature. But both brushing and swabbing will give uneven thickness because they are highly manual. Plus strives or the brush marks will be visible on the casting. Many of you who have made these large iron and steel castings would have seen this. Brush marks, they don't level off fully. They also depend on the skills of the operator. You need a skilled operator to get as smooth and even surface as possible. Sometimes, because you are physically rubbing the paint, especially in brushing onto the surface of the mold or core, there is a chance that some sand will come out or some reaction would happen, and that would create undesirable surface for mold and core and will cause metal penetration. If for some reason you are required to use solvent-based or spirit-based coatings for large molds and cores, then a technique called painting by parts has to be attempted or has to be used. What attempted? Has to be used, because if it is very important that after the coating has been brushed or swabbed, you should immediately light it off so that the binder in the coating becomes effective and coating will adhere to the surface of the mold or core properly. If because there is a big mold and you keep on painting and the first painted portion, the alcohol gets evaporated, then the bonding of the coating to the sand substrate will not be adequate and you may get coating getting washed off and associated casting defects. So this technique of painting by parts and then immediately flaming it off is necessary. For very large castings, sometimes 2 layers were required to be applied. Then generally the first layer will be used with a slightly thinner consistency. So whether it is water-based or alcohol-based, you would make a slightly thinner viscosity and then apply the coating. That would allow the fillers to seep inside the coating layer and you will get some depth of penetration into the sand substrate so that you ensure that the voids are filled to the extent possible and then give a top layer. We have an example of a very large casting towards the, as we go further in this lecture. And coating thickness, how much coating thickness one should have? Whether you want it to be some 300 microns, 400 microns, etc., gets decided by two things. It is by experience. One is how open is the sand surface and how large the casting is. What is the metallostatic pressure that will be seen? Because both these factors go back to the mathematical equation that we saw earlier. Balance of forces between the metallostatic pressure and dynamic pressure versus the frictional resistance and the capillary action forces. The swab is most useful aid in coating the interior of difficult pockets because it is flexible and re-entrant angles, which is slightly difficult when it comes to using brush. It will be fair to say that in more organized foundries these days, brushing and swabbing is getting replaced with slightly higher production levels. It is gradually getting replaced by the flow process because of its inherent advantage of more even surface and better casting finish, etc. Now, spraying of the liquid, this is another very popular way. The productivity is high It is much faster. But what is important is to pay great attention to the coating composition. That means what is the viscosity of the coating that you will keep. So it is a fine balance between your ability to suck the coating into your spray gun and pushing that filler onto the surface of the mold and core. So that fine balancing has to be done. Spraying methods use specially designed guns to atomize the coating into fine spray, and what we see here is what is known as typically triple action spray gun. It uses the principle, see you have one of the nozzles goes into the the tube which is attached to one of the nozzles goes into the coating container, other is attached to the compressed air line, and as you press the wall, because of the partial vacuum that is created, the coating gets sucked from the container and comes into the nozzle and gets sprayed. Now, why triple action? One is this action of sucking the coating, and second action is spraying, and third action will be if you block the nozzle with your finger, then the air goes back into the container and helps stirring. So there was a practice of spray and then periodically ensure that the coating inside the container is homogenized by closing the nozzle and stirring the coating through compressed air passing through the coating bath. One difficulty with spray, with compressed air spray guns is that in deep pockets, because of the back pressure of the air, the refractory may not get deposited properly in the mold or core cavity. Now, that issue can be taken care. So unevenness of the coating layer can become a problem, especially if you have a complex geometry for your core or mold. Now, system of airless spray guns has come in. That is what is presented here, where compressed air pushes the coating down. There is a stirrer also inside to ensure that the coating remains, in a homogenized state, and that pushes the coating through a spray nozzle, and you get airless spraying system. One advantage I have personally experienced this in the past, where very highly viscous 70% solids containing coating also could be sprayed by using these kind of airless spray guns. But maintaining them is very important. Maintaining the spray guns, maintaining the consistency is extremely important. The airless spray guns obviously sort of improve the efficiency of transfer of fillers onto the mold and core surface, because there is no air which can, there is no back pressure of the air involved. Now let's have a quick look at the video of this spray. I think this is from a Brazilian foundry long ago. It's an old video. As you can see, this gentleman is spraying a coating. It is a carrier-based coating which is being sprayed onto what looks like a base core for a cylinder head. And he is flaming it off, as you can see. But the important points to be noted are that a lot depends on the skill of the operator. So non-uniform coating application in deep pockets and flanges, etc. Say you are going to do a wall body or a pump casing, then flanges which are deep may not get coated properly. It also may mean non-uniform drying due to solvent loss. We saw him flaming it off immediately, but sometimes if there is a delay, if the workers are not well trained, then in the spray solvent goes away, and if you don't flame it off in time, then you will get non-uniform drying. Also, in spraying process in the deeper cavities, you may find that coating can accumulate and may lead to problems. And as all of you can make out from the video, it's not a very environment friendly process. A lot of carrier comes out into the air. Now, a few words on this. This process is called electrostatic or tribostatic powder spraying method, also designated as EPS method, electrostatic powder spray. Now, in this process, surface of the substrate is first made conductive. If it is not a conducting material, by spraying electrically conducting polymer solution on them, then the powder coating can be applied. The people who have developed this, they say that it can be used against all the very popular binder systems such as PU cold box or hot box or furan or inorganic types. I had, like I said earlier, I had some experience of this, but it was on green sand, where because water is a dipole, we could apply the coating onto the surface of the green sand mold. Now, the application that we had chosen was a high pressure molding line making engine block casting. And as I said earlier, it is very common to spray a coating, a spirit-based coating, to get good surface finish by avoiding metal penetration in those cases. And we had tried this. It did work okay in trials. However, for regular usage, it calls for high level of automation. It calls for very high level of automation. Now let's look at dip coating, which is one of the most popular way of applying coating, especially on cores in mass production units, whether it is automotive, particularly automotive, or even non-automotive, but where the numbers are large and cores are small. So very simply, dip coating technique can be described as a process where substrate to be coated, that is your core to be coated, is immersed in the liquid or a coating and then withdrawn with a controlled speed under controlled temperature and atmospheric conditions. See, you have to keep in mind that you go to Europe or some parts of USA, say many parts of the world where the winter conditions can be very, very severe. That's why this mention of controlled temperatures and atmospheric conditions. Now, coating thickness increases with faster withdrawal speed. The deposited thickness is determined by balance of forces at stagnation point on the coating suspension surface. We have a diagram after this to see. Faster the withdrawal speed, the more the coating suspension is pulled up onto the substrate surface because there is no time for suspension to flow back. So here is a picture. You have a coating container, a tank in which there is a coating. A core has been dipped inside and it is being withdrawn, and you can see from both the sides, the schematic, the coating is adhering onto the surface. Now, all other assumptions are there that you have your proper wetting agents and balance is there. Otherwise, I have a video. If certain surfaces are very water repellent in nature and you don't have proper formulation, then coating will not stick. So here, while explaining the principle, it is assumed that the coating is well balanced and we are explaining the mechanism. So as the core goes up, this much layer will remain, and anything excess, the stagnation, beyond stagnation point, it will fall back into the coating tank. Now let's have a quick look at what normally we would call as a slightly crude way of dipping the coating, manual dipping, that too for spirit-based coating. It is meant for manifold. The video is taken for manifolds. Very quickly, let's have a look. I know the video quality is not great, but you'll be able to see the essential. See, what are the important points? You saw him shaking the core up and down to remove excess coating. This is obviously a spirit-based wash. Then details of the dip tank are not visible. What you would have noticed would be the level of the coating inside the tank is just adequate. This is from safety point of view. Then precautions have to be taken to avoid fire risk. That is why as minimum possible as spirit-based coating is being used for the tipping purpose. Plus, flashing off area is away from the dip tank area. It is separated out. So environment and safety are the main concerns while using solvent-based coatings for dip application. So you need to make these formulations very, very carefully. And if for some reason foundry doesn't want to flash out the coating, then you will have to use specialty formulations by using a combination of carriers as well as specialty binders. I will not spend time on. I had a personal experience of developing such a coating for engine block castings long ago, when we were working very closely with Tata Motors for coating the cold box cores for side cores of the engine block. Now, what we saw was a very manual operation. Now, what we are about to see is a little more level of automation. And here is a video of what to me looks like a base core for cylinder head. You can see a tackle being used. There is a simple arrangement to ensure that the core gets dipped up to a particular level. Then excess coating which is coming onto the face has been wiped off. Then core is being rocked to remove the excess coating. Inverting the core also ensure that excess coating gets removed from the vents. And in close-up, you will also notice a good stirring arrangement whereby you can see that the coating is kept in very well mixed condition. And now we can go over to the third type of a very robotic application. I know I have received a comment here, can I expand it? While presenting this now, I cannot expand the view. I will have to redo the presentation itself. So here is a case of robotic dipping of a ventilated brake disc core. There is a core shooter, then adjacent to that is this robo which is picking up the cores from the core box. They are getting trimmed. Then they are spinning, they are rotating as they get dipped inside the coating bath. Then the other two sets, so all of them are getting spun at least 3 times. It is also tilted to ensure that excess coating goes off, plus again it is spun again. And then it will be placed for drying immediately. So trimming of the cores, rotation and spinning of the cores while getting dipped, tilting of the cores after removal from the tank, as well as spinning once again. So that is what is required to ensure that there is a uniform coverage. Here is another video of dip coating of tractor transmission case. You can see how carefully it has been planned. The excess flow of the coating is happening from this area. You see these two motors where stirring is happening. In between them, you will find excess flow is going back. Core after dipping is being shaken, held for some time for excess coating to flow off, drip back into the tank, and then it is immediately being placed into a continuous drying oven. So the key aspects, as all of you would have seen, it is usually used for cores and is well suited for automatic applications. And big plus point is high production rates and very high transfer efficiency, that is transfer of filler onto the core surface as compared to say something like spraying, and it is amenable for automation, so labor required is less, and by very nature even complex shapes can be given a very even coating. Now, what are the key points? The effectiveness of dip coating process depends greatly on managing the density, the surface tension, and the viscosity of the coating. That means wettability, viscosity, and density. Density is a surrogate measure for how much is the filler content. Surface tension is the measure for wettability of the coating, and viscosity is the ease with which the coating will cover, the coverage, ability to cover the pores. Even thickness of surface is necessary so as to maintain dimensional accuracy and true reproduction of contours. I mean, those of you who are designing patterns and core boxes, you are already familiar that while designing them, to ensure that casting dimensions are finally met, you provide allowances for coating thickness as well. Now, dry coating thickness needs to be decided for dimensional consideration, as I said, but it is difficult to measure dry coating thickness without disturbing the coating surface layer in the process. So wet film thickness is worked out by considering solid contents of the ready to use coatings. So as an example, we'll see a wet film thickness gauge, but I am saying if you have X as the wet film thickness and you have 50% solids content, then we can fairly assume for a even coating, the dry film coating thickness will be half of wet film thickness. So that is verified by the foundry during the initial setting of the process. The viscosity of the coating must remain practically constant if the deposited film quality is to remain high and the same. So to maintain the viscosity, carrier must be routinely made up. So your equipment design has to take care of this, or if you are doing a sort of manual operation, continuous viscosity, periodic viscosity measurement, and then adjusting the viscosity by either adding the excess wash or excess water needs to be done. I'm getting comments. Now, coating thickens with exposure to the air if it is spirit-based coating especially. So it needs to be managed. Even water-based coatings, if they are exposed to, especially in say summer season, they will tend to thicken. So that needs to be adjusted. Usually dip coating will not be suitable for objects with hollows or cavities because it is difficult to control the coated thickness and drying it. Now, Water-based coating must be used within the specified shelf life, because as we have seen in our last lecture, there are organic binders which are used for, these are the binders for coatings, and they can degrade. So usually the manufacturer will be recommending how long a ready to use wash can be kept. Otherwise it needs to be discarded, because with biodegradation, the properties of the coating will also deteriorate, and it will create problems. Another housekeeping aspect is this, again, I'm sure the coating manufacturers will be recommending. There has to be a proper cleaning schedule for the equipment which is used for dip coating, in order to prevent any fermentation happening in the tank. Now, a slide on what are the defects in coatings. One defect in the coatings can be, it depends on the formulation and type of the mold and core surface, and non-adherence of the mold to the mold and core surface. It can happen mostly in water-based coatings, and this needs to be taken care by use of proper level of wetting agents in the formulation. Now, synersis is another defect in which water oozes out from the coating layer and it carries filler away, like almost like a canal on the core surface. So that is an indication that gel system needs to be optimized. Our people who do the formulations, they call it as control over flocculation, deflocculation tendency of the gellants. Then uneven coating at its first, when it runs down as tears. And this depends on the nature of the surface to be coated, but mainly depends on how well balanced your coating suspension agent is. Tears and similar coating faults are sources of high gas evolution also, because there will be accumulation of the coating. So one needs, the user as well as the manufacturer of coating needs to take care of these. Let's have a quick look at dip coating equipment. Now, dip tank designs are usually customized for a given foundry shop, depending on the type and the size of the cores which are going to be used, going to be dip coated. The geometrical dimensions and shape of the dip tank needs to be done. Usually the tank will have a balancing reservoir to ensure constant table in the dip tank. There are 2-3 ways in which people do this. We will see it in the next couple of slides. Now, continuous agitation or continuous mixing of the coating must be ensured by use of either a diaphragm pump or stirrers located at right place in the tank. This is very, very important. In other words, there should not be any dead zones in your coating tank. Now, usually these coatings will be in circulation. So as the coating goes from the dip tank to the balancing tank or a mixing tank, then a filtration device is necessary, because it is unavoidable that some amount of sand coming from the cores will get introduced into the coating. So during recirculation, it must get filtered out. Otherwise, you will have defects coming, because the loose sand particles will come onto the surface of the mold or core. Now, B4 cup with various levels of automation is a very popular way of adjusting the viscosity of the coating. Now, depending on the formulation of the coating and the type of the core and the quality of the core, people will decide what level of viscosity, in what range the viscosity must be maintained for dipping application. And for automation purpose, densitometers are also available, so that more or less constant consistency in terms of viscosity and solids is maintained. That is very vital because that is what carries the filler onto the surface of the core. Here is a picture of a small setup. You have your dip tank here, as you can see, and there is a stirrer motor here. Now, this is the overflow which goes back to this, what I call as balancing tank. This is the coating mixer where fresh coating is prepared, and as per the need, it will be added here into the balancing tank to maintain the consistency. And it is being pumped back. You have a diaphragm pump sitting here, which will be sending the coating back into the tank. So the coating is being sucked. Sorry, I gave the reverse sequence. The coating comes out from here and then goes up there. Another sketch here where you have a working tank. This is sort of top view, where after the dipping of the core, some overflow will take place, which goes into the collection tray, and overflown coating goes into the preparation tank or a mixing tank, where the consistency will be adjusted and it will be pumped back into the working tank. Here is a picture. This is from one of the Brazilian foundries, and you can see here actually a robotic arm and a core is being held here. It looks like an engine block package, core package. Here is a densitometer. These are the stirrers. This is the close-up of a densitometer in the tank. So this is in brief about the dip coating for small and medium sized cores to be done in large numbers, and we saw a large variety. We saw manifolds, we saw engine block cores, and we saw cylinder head cores. We also saw the ventilated brake disc cores. So a large variety can be coated in this way. Now let's come to medium and large molds. The size is large, but the numbers are less. In the old days, they were typically sort of coated by using either brushing or swab. And now what is being used is flow coatings, and here are a couple of pictures. As you can see, a man using a hose is applying a coating onto the surface of the mold. Let's look at the details. Why flow coating? We saw one of the drawbacks in case of brushing and swabbing is it is highly manual operation. You can get brush marks, you can get uneven coating thickness, which can result in uneven casting surface finish. So flow coating allows you to have consistent layer thickness on both horizontal and vertical mold surfaces or core surfaces. Deep and normally inaccessible parts for brush and swab can be easily coated. It is operator independent process. I won't say 100% without operator, but very less skill is required. So casting looks better, aesthetics is better, surface finish is smoother, lettering and numbering details are very, very sharp. This is especially true in case of castings like valves. And productivity is high as compared to brush or swab or even spray. Flow coating gives you higher productivity as well, and consistently better casting surface finish. Now, what is flow coating? Flow coating, in simple words, is a method of applying a refractory coating that can be described as wetting the molds or heavy cores with garden hose at low pressure. High coating transfer efficiency, 90% and higher. For flow coating to be effective, it must create surface and subsurface coating. We will have a look at that little later. What it means is flow coating has to penetrate inside the substrate inside the mold and core surface so that coating gets anchored, and plus you have on the top of the surface also coating. We have a case study which explains this further. Surface coating provides a barrier to the metal and improves surface finish, and subsurface coating, the filler which has penetrated within the cavities in the sand grains to fill the voids between the sand grains, it reduces possibility of metal penetration and wearing. Now, in case of flow coating, again, dry film thickness is, we saw as in case of dip coating. What matters finally is dry film thickness, and that again depends on coating viscosity. Now, with flow coating, the mold and core is maneuvered by using either manipulators or by overhead cranes, or sometimes relatively small cores you may do them by hand as well. So it is held at an angle of 20 to 40 degrees to the vertical in front of the operator, and coating is applied through the hose. We'll see a few pictures. Now, when you're coating, you will start at the top and then move the hand laterally, move the hose laterally, and progressively come down from top to the back. So this can be used easily for odd shapes and big shapes, where you cannot use dip coating because of the size involved. Now, coatings applied by flow coating have only poor or fair appearance unless the parts are rotated during the drippage. So that is where the manipulators come in, or skill of the crane operator comes into the picture. That after hosing this coating onto the surface, still there will be coating will be flowing down. So in order to ensure that you get a smoother finish, you have to allow the removal of excess coating through drippage by either moving the mold by using the holding mechanisms, as well as physically removing excess coating, as you will see in some of the pictures later. Now, the flow coating is very fast and easy. Requires little space, but yeah, it does require space for having a collection tray and a stand for keeping your molds and cores. Involves relatively low cost installation, maintenance is low labor requirement, and operator skill level also is low. And here are some examples, some photographs. Now, here is a typical flow coating station with a pit here, because the coating, the excess coating flowing down will get collected, and it will get recycled after filtration and adjustment of the consistency, etc., etc. And this is the stand on which the mold will be kept. Like you can see, the operator is lowering the mold onto the stand. After lowering it onto the stand, you can see the chains for overhead crane, and then he is applying the coating onto the mold. Then excess coating is sort of shoveling it away, or raking it away, getting wiped off, and then the final coated mold is ready. Now, a little more automation. In a fast loop line, you have got mold handlers. As you can see, it is being held at an angle, and they will get as the coating progresses. Now, let's quickly look at one particular case where a specialized coating was developed by a supplier. This is a case study which has been taken from foundry practice issue of Paseco International. This is about MAN marine engine block. Now, it's a large crankcase weighing in excess of 100 tons. In section thickness, is 200 in excess of 250 millimeters, so greater than 10 inches. Now, as this foundry was making these castings, it's a European foundry, they were facing problems of burn-on and metal penetration defects and, poor peel-off. Poor casting releases, another word used is peel-off from the mold. Casting getting peeled off easily. That was essentially because of the, improper mold and core coating rheologies. Now, in such cases, coating layer thickness is the key control measure. So, as the case study says, this particular manufacturer and the supplier, Proseco, they worked as a team to overcome the problems of the burn-on and poor metal penetration, etc., that they were facing. Now, they defined what were the requirements. One is they want consistent coating layer across the whole surface, uniform coating on mold material, chills, and pre-coated area. There are different types of binder systems being used for cores and molds. So, because the cores and molds are so huge, they wanted to ensure that for a good leveling purpose, they have to have long, what is termed as a mat time, the coating freezing time. Then they wanted same coating to be used for dip application as well as over pour application. That means same filler combination was to be used in all the cores. So they wanted it to be applicable for both no-bake for molds and PU cold box for cores. Obviously, good suspension properties is very vital for this. The coat, because it is going to take a long time, stability also of the coating formulation was very important. External influences would mean, environmental factors as well. Both medium and large cores were to be used. Suitable for highest thermal demands, which means you have to choose your filler combination very carefully. As you can imagine, more than 100 tons is the weight of the casting. So section thicknesses are large, the size is large, so head heights will be large. So fillers to be chosen and the way in which the coating will get applied. They have said in the case, both the coating had to be suitable for dipping application as well as flow application, obviously by adjusting the consistency, but filler combinations will remain similar. Now, when handling such large molds especially, one has to remember that with such huge molds and even in cores, not all the areas of the mold, despite best efforts, will be compacted to the same level. The openness of the surface will vary from location to location depending on how the compaction has happened. And that means there will be the risk of metal penetration in the area of low compactions. This will be governed by the geometry and the flowability and the technique of filling the sand, because usually the mixed sands will have a particular shelf life. So if you don't fill the mold in the correct time, then as the bench life starts going off, the flowability of the sand becomes an issue. So packing will become a problem. And here is a picture, as you can see, of how the open surface looks like. Now, to overcome this issue of uneven compaction and openness of the surface in some areas, then they designed a coating to penetrate the core surface and deposit sufficient quantities of zirconium silicate in this case, in these cavities, sealing them, and then either eliminating or reducing the metal penetration. So, a base coating in specific areas sort of anti-penetration coating you can call. And then after the coating has penetrated inside, then you need a layer thickness of 300 to 350 mm for ensuring good peel off of the casting from the molding material. This is the core. You can see block cores and you can see the size, 100 tons. You can see the person who is flow coating what looks like to me the crankcase cores. So huge. Now even layer has to be seen or replicated in both horizontal and vertical surfaces. So after coating, to ensure that there is smoothness, a low pressure, a partially pressurized air is applied in specific areas of accumulation to remove excess coating from horizontal surface and deep pockets. Now here is a comparison between their practice which was earlier followed in the first column, and next column is the properties of the coating which got developed for meeting their requirements, previous practice and new practice. One of the important parts was the sedimentation rate over 24 hours as a percentage. See, their earlier formulation used to have 17% separation, while the new formulation had excellent suspension, so just 1%. Flow lengths were very similar, so flow properties were same. But look at the big difference in the mat time. That allows for leveling of the coating. So earlier the mat time was much faster, 33, against a new practice which is 222. Ring test, I'll not get into the details of this. It is something which tells you about the how well flocculated, how well dispersed the coating is, how well dispersed the fillers are in the coating. Then layer thickness after dipping, 5 seconds dipping, and the coating penetration after 5 seconds dipping. As you can see, the new practice that they followed had a better penetration as compared to old practice. Then as a result, on the top, the coating thickness layer will be slightly lower, doesn't matter, because it is a combination. The metal penetration is being resisted by the filler which has penetrated inside the mold and core surface. So this is one example. Now, oh, okay. I'll have to move faster. Drying of the coatings. In case of organic solvents, which are now going out of fashion gradually, people earlier, for safety reasons, were trying to do self-drying, but torching and flaming also is done. But for very large molds, that presents a peculiar problem. For very large molds, if there are accumulation areas, then the binder may get affected because where the excessive carrier seeps inside the mold and core, especially in corners and pockets. So generally for environmental health and safety concerns, organic solvents are getting out of fashion. Trend is for water-based coatings, which require longer drying time. Drying temperature has to exceed 100 degrees centigrade, but it has to be lower than 250 degrees, otherwise organic binders will get destroyed. There can be various techniques which can be used. It can be high intensity lights or microwaves or drying tunnels and infrared ovens. The experience has been that high intensity lights and drying tunnels many a times will not dry fast enough. So the dripping of the coating can happen and thickness of the coating can become non-uniform. Microwave drying uses non-selective heat, and sometimes it can cause disintegration because it is something with it. As all of you are familiar, microwaves are very familiar. It is by molecular friction. So within the core or mold itself, there will be intense generation of heat, and it may cause degradation of binders and cores. Binder and then the cores and molds. Infrared ovens, they are very good. They will dry very quickly without damaging the sand. The drying times can be reduced by as much as 85% is what experience says. Energy saving comes from controllability of the infrared unit. I'm going through quickly because we have lesser time now. Now, infrared elements will direct the heat more effectively at the mold and can dry the deep cavities. So, better casting quality. And it uses lesser floor area as compared to whether resistance ovens or any other big drying ovens are there. Another thing which has happened in coatings technology is color change. So color of the coating changes once it gets dried, as you can see in the picture here, from pink to yellow, which is an excellent aid, especially when you are handling large molds and cores, to ensure that it is a good quality control tool. It will also help in conserving the energy. Now, a few quick slides on coating checks. Specific gravity or density, and you can use this density cup for measurement. Bomb. I'll not show the video here, so we are short of time now. But what is important is how do you measure the bomb? You have to hold the bombometer and allow it to lower slowly into the measuring cylinder in which you have taken the coating. You cannot drop it or you cannot force it inside. Otherwise, you will get erroneous reading. I think I'll skip the video here since we are running short. Sedimentation is pretty straightforward here. Measuring cylinders, you stand them at the application consistency for 24 hours and measure the separation. B4 cup viscosity you can see. So you have to usually these cups not only in laboratory for quality testing for incoming material, usually you will have these on the shop floor next to your dip tanks or your flow coating units. Now, measurement of wet film thickness, such gauges are available. So the sequence of picture shows how do you measure. You take it to the right angles to the surface and place the core and look for which slot matches with the thickness. So you look at which slot is wetted and you know what is the wet film thickness. Now, coating penetration depth is evaluated by cutting a core, but this is a sort of destructive test that one can do in the laboratory. So a representative core can be taken and either dipped and dried and seen how much is the penetration, whether it is 2 sand grains, 4 sand grains, like that. As we have seen in our previous example, as the penetration increases, the proud layer, the layer on the top surface will obviously decrease. So there has to be an optimum between the two. Too thick a proud layer also if you go, then you will find it flakes off and creates problems. A quick picture of what happens. When you are spraying, you will get a thickness which is relatively less. By dipping and flooding, you will get a good level of penetration of the coating inside the core. Brushing gives little more than spraying. Now, coating permeability, very quickly, I will not even read this slide. I will make only 2 points. Coating permeability can be used in 2 ways. When there is a lower permeability level, then you can direct the gases coming out of the burning core through your vents into the print areas and take them away. While this is where the coatings with lower permeability are useful. And coatings with higher permeability are when you have to remove the core, or in case of evaporative pattern casting process, You have to exhaust the gases of the pattern itself, which is getting replaced by metal out through. So you need special formulations for that. What one should remember is permeability of the coating as tested on say a 2-inch by 2-inch core in the laboratory by using permeability meter at room temperature could be different than at high temperature, because there will be a degradation of the coating layer. Now, a few quick points on core degradation. The carrier of the coating can attack the binder system, as we discussed earlier. So longer the core stays wet, more can be the degradation. So it is essential that we send either flame off for spirit-based coating, or we send it into a drying oven for water-based coating as quickly as possible. Many coatings will use surfactants as wetting agents, and they will increase the penetration of the coating inside the core surface. So that one has to be very careful. And third bullet talks about setting up specification for how much degradation of the core strength you would allow. So you can have a quality sort of specification set for the coating supplier, saying that when I apply your coating onto a say a doggone core, then after drying the strength should not drop beyond so and so limit. That is very common. Loss in strength is what is specified. So in summary, coating selection and application methods depend on metal being cast, the size and shape of the casting, number of molds and cores to be made, and facilities which are available in the foundry. Many times customized coating formulations are needed to meet the specific application requirements. Process control on use of coatings is vital for consistent performance. Good control over the coating equipment design and maintaining its hygiene and good working is very, very important.